My name is Mick, and I'm Australian who lives in Norway. I've been there for 12 years. I'm a programmer in that company, Finn, for the past 4 or 5 years, working on back-end systems, systems design, core and data platforms. A little bit about the company Finn. It's Norway's busiest website. It's a classifieds website. It has the vast majority of classifieds and traffic in every single vertical of classifieds. So we're talking about real estate, job listings, cars, boats, motorcycles, bits and pieces, cheapest flights and cheapest hotels, services, professional and amateur wanted and on for sale. Only other country in the world which has that dominant position on all verticals on one website is in New Zealand. You can see we're in quite a unique position there. That we're basically sitting on the country's online buying and selling experience. The story behind Finn is also quite interesting in that in '99 it was started up by the country's largest media corporation. So it was a startup with the intention of taking the classifieds away from the newspapers and putting them online and cannibalizing its own profits. That was a hugely successful adventure, and it's led to 2 things. One, that media corporation, Schibsted, is much to the envy of media corporations around the world as the newspaper profits plummet. And 2, it has led to Schibsted heavily investing in classifieds throughout Europe. So you may recognize some of these websites. They're all a consequence of Finn's success. About 3 or 4 years ago, we started to modularize our monolithic Java and Sybase application into what you would refer to today as a microservices platform. And one of the first modules that we had to pull out was around statistics that we show back to the users. Now, these statistics previously, just for collecting the numbers in their totals, was already taking up 50% of the database's write CPU time. In fact, during peak traffic, if there were any problems in production, the first thing that operations would do would be to turn off that write procedure. So when users were getting the most traffic and the most statistics, we had to stop counting. So we evaluated different scalable databases. And when we looked around, there were 3 things that we looked for. We looked for the feature list of those databases. We looked at the quality of the code in those open source projects. And we looked at the quality of community in those open source projects. And at that time, there were really only 2 choices based off those criteria. And that was Cassandra and HBase. For that project, Cassandra hit the sweet spot. And we are so incredibly happy that we picked Cassandra because it's a technology which just keeps on coming leaps and bounds. We keep on writing all these workarounds, thousands of lines of code, and then the next version of Cassandra will come out and completely remove that constraint from the system. We're just throwing away code. We don't need that anymore. It's also a database which keeps on getting faster. Once we nailed that module, and it was quite a tough module for us to nail. It wasn't just new technology Cassandra, it was a new technology Hadoop and Scribe. We were also dealing with brand new paradigms in our development, asynchronicity, scalability, fault tolerance, circuit breakers, we were still very new at the microservices platform and trying to change the whole organization to adapt to it. But once we nailed it, we found that with this established Cassandra platform in the company, it wasn't just our big data platform. It was also incredibly suited to all these other simple use cases that we thought lived in the SQL world. And especially in the last 12 months, we've seen an explosion, a doubling of use cases coming into Cassandra. Often quite simple, small things, but they just work so much better on top of Cassandra. So today, here are some of the things that we use it for. And because Norway is a little country, well, and here are some of the comparisons from going from SQL to Cassandra. Write improvement is always there. When you go to Cassandra, writes are always faster, and we see 10 to 100 times improvement in write performance. Reads, well, we're usually bringing over the schemas which make sense in Cassandra. And when they make sense, everything improves. And reads can too. In some use cases, so we've gone from Sybase or Postgres over to Cassandra, we've seen a 20-fold improvement in read performance. This year as well, we've seen 1/3 the number of serious production incidences compared to our SQL databases. Norway is a little country. In the other room, you have Apple talking about 10,000 nodes. And here, we're talking about 8 nodes. Part of this talk is to show you how much you can do with a small cluster. And I think it's also a relevant journey to share because this is where people start. You start with a small cluster, and the things that you learn on a small cluster stays with you as your cluster gets bigger and bigger. We have 8 nodes, and of 6 of them, they're bundled with Hadoop and Spark. Now, the Cassandra recommendation is to have separate data centers for offline and online use cases. We don't have enough nodes to properly follow that recommendation. So we've got all of our offline and online applications in the one cluster. But to ensure low latency times for the online applications, we've got these 2 nodes that don't have Hadoop on them. And to do that, we ensure that they're each sitting in their own virtual data center, so that the online applications has a replica always on those nodes. And then we leave it up to the cluster's snitch and cross-node timeout and the rapid read protection to ensure that the requests will always go to those online nodes if Hadoop is really bringing the other nodes down to its knees. In 2015, we have a budget to move towards something like this. I did forget to mention that this is dedicated hardware. So it's quite beefy machines. That's another reason we have a smaller cluster. And it also takes time for us to get new nodes. We have like a 3-month turnaround for every new server. But in 2015, we'll be moving towards a larger cluster like this. We really need it. We are over capacity at the moment. And what we will do once we have 3 nodes in each of those online virtual data centers is that we will fall back onto Cassandra's recommendation and create a proper separation between the online and offline applications. So for the rest of the presentation, I want to just dive into that first module that we wrote, event statistics, and how we use Cassandra and Hadoop together. So like I said, these are the statistics that we show back to the users. So when a user logs onto the website and they go onto the page which lists all of the ads which they are trying to sell, on each of those ads there are statistics like how many people have seen your ad, how many people have sent an email about it or marked it as favorite. When we sat down and we went to design something new, it had to be asynchronous, it had to be scalable, it had to be fault tolerant, and we also wanted to open up the world, open up a new world of possibilities as to what we could do with these statistics rather than only collecting the totals. What we came up with was something like this. So we have an event tracking or collection system. So events can be generated anywhere in our platform or on the devices, and they'll come through like a web tracking REST API or from within the platform directly into our message bus system. There they'll go to Cassandra, and then we put those events directly in as is, as time series data, into Cassandra. And then on top of that, we have Hadoop jobs constantly aggregating the data into different statistical views. And then we have separate modules just to serve those ready-to-go numbers to the applications that want it. This, of course, has opened up what we can do with statistics. Here are a number of screenshots that we've got. Top left-hand corner is statistics for one particular ad over days, and all the different types of statistics, page views, emails sent, etc. The middle in the top is page views for one particular ad by day in a column, stacked columns, which show which variant of the website was used, the desktop or the mobile website, and against which client device was used, Android, iOS, desktop, tablet. Underneath that is the same graph, but this time broken up by referring domain. In the bottom left-hand corner, with the horizontal bars, you've got repeat visitors. So the bottom horizontal bar is how many people have seen your ad once. The bar above that, how many people have seen your ad twice. Above that, how many people have seen it 3 times. It gives you a good intent to the seriousness of the buyer. On the very right-hand side, you've got a screenshot which puts a lot of these statistics together from a mobile app that we've written. And in the line graph, you see the page views for your ad overlaid onto average traffic pattern. And that average traffic pattern line, you can choose. For example, if you're selling a house, you can say, what's the average traffic since the ad got published for a house in Norway, or for a house in this price range in Norway, or for a house in this price range in this suburb. So I'm going to step into the individual pieces of this design. First up is the event collection side of things. At this point, people often ask us, how come you didn't do streaming? How come you went with the aggregation approach? And there's a number of reasons for that. First of all, when we started 3-4 years ago, these technologies were still quite new. And we wanted to open up our horizon, and we wanted to work with just Cassandra and Hadoop. We knew if we introduced too many new technologies, we'd end up with a solution which was inflexible rather than opening up our horizon. We also knew that there would be statistics which we couldn't do with direct streaming. We also knew that we wanted to be able to generate new prototypes of statistics on existing data, often months' worth of data. So the events which are created are very simple. In our microservices platform, we either have REST services or we have APIs defined by thrift. Everything that goes into our message bus system is defined by thrift. So here we have a very simple thrift bean. 3 values, type, subcategory, properties. So for example, a page view to an ad is type ad, subcategory, page view, and the properties are going to have the ID of the ad, the ID of the user, the browser type, the device type, etc. The message bus system was originally Scribe. Scribe hit the sweet spot for this project. It's very resource efficient, but we've moved away from Scribe and to Kafka for a number of reasons. 1, Scribe was pretty much a dead project. 2, it didn't give us a combination of fault tolerance and load balancing that we expected it to. At the same time, in our microservices platform, Kafka was chosen as the message bus solution. And it certainly comes with a lot more options. For example, now we can also do direct streaming of those events. But Kafka uses a lot more resources. While Scribe daemons were originally just almost invisible processes running on every machine, we now have a 5-node Kafka cluster. And you compare that to an 8-node Cassandra Hadoop cluster, where we're actually putting Hadoop jobs in and running them there. There's kind of an odd comparison to efficiency of resources. Also, Kafka uses Zookeeper, which is kind of unfortunate when the asynchronous component to your service-oriented architecture is built upon a CP system. And in a situation like us, where we've only got 2 physical data centers, one of those physical data centers go down, and all message bus consumers stop. It's like, oh. When those events come into Kafka, they come into a schema like this. The petition key is a time bucket. And the time bucket is the current minute of the current day. And then each event comes in with a timestamp and then the 3 fields from that bean. Maybe you see something wrong, because the real world ain't that simple. Having that hot petition key is a bad thing to do in Cassandra. It's an anti-pattern. All of your writes going to the one petition key at any moment in time, it's not something you want to do. We solve that by inside the petition key, adding an extra column called petition, and that's just a single random digit. And as long as the number of values you've got in that column are greater than, especially a factor of the number of nodes you've got in the cluster, then you've got an even distribution of writes around your cluster. The other thing in the real world is that there is in fact 2 timestamps. There is the real timestamp for when the event happened, and there is the timestamp that it got collected in Cassandra. So all of those incremental aggregating Hadoop jobs, they're interested in what are all the events which have come into Cassandra since the last time I executed. Whereas if I'm writing an ad hoc query, for example, how many bicycles were sold in Oslo for 200 kroners on the 17th of May, I'm working with real timestamps. But for the slide after this, I just want to work with the simple schema. So next up is the aggregation jobs, the incremental aggregation jobs. When a MapReduce or Hadoop job runs, it hits Cassandra in 2 places. When the job fires up, it's got to talk to Cassandra and say, for the data that I'm interested in, can you generate splits for me? Those splits become separate tasks, and then the job tracker will send the tasks out to different task trackers in your Hadoop cluster, and each task, when it starts the mapper, will then load data from Cassandra in chunks for the split that it's responsible for. Now, for us, with the schema that we're using for the events, we don't need to go to Cassandra to get the splits, because those minute time buckets, they are good splits for us. Otherwise, when the mapper starts up, it's always just taking slices from inside one row and working with that. Really important aspect of this is data locality. Things here have come a long way with SQL. SQL has really changed this picture for us. The SQL driver will favor a localhost coordinator, and with a consistency level local 1, always be reading data from the local data center, and that helps a lot. But the problem can't be solved there, because it's about the capacity scheduler in Hadoop and how it sends out tasks. Each task comes with a list of locations where its data can be found, or where the replicas sit. And the job tracker will try and send those tasks to those task trackers. But if they're busy and there's another task tracker free, it will just send it to the free task tracker. So you're only going to get data locality of 60, 70, 80% a lot of the time. You can fix that by using the capacity scheduler and setting up this node locality delay. For example, if you set it to 3, what it does is, instead of sending that task to any free task tracker, it will instead put the task to the back of the queue and try and send the next task somewhere. And once the task has been through the queue 3 times, it will then just give up and send it anywhere. With that solution, we see data locality rates well over 99%. And we see at times the difference means a throughput 4 times greater. A lot of the aggregation jobs that we have, especially just about the statistics that most of the statistics that I showed, they're just glorified word count examples. There are maps of maps, because we're doing lots of statistics in individual passes, and they are incremental. And the way we do that is that they'll generate the numbers for a given period and then take those numbers and just dump them on the statistical views, which is the counters in its own key space in Cassandra. Each day we're running over 5,000 continuous Hadoop jobs. Those Hadoop jobs run in about 10 to 15 seconds. So you can kind of see that we're breaking down the technical separation between what is streaming and what is aggregation. The streaming solutions, they also do batch. And this is just continuously running job. Yeah. But these jobs can catch up after a period of downtime or maintenance far quicker than streaming solutions can. They can tackle days or weeks worth of data very effectively, or just the last minute of data. We have numerous nightly jobs, we have ad hoc jobs. Each day, even when we only had 4 Hadoop nodes, we were reading about 1 billion records a day out of Cassandra and writing back about 150 million records. So Cassandra can do a lot for you. You don't have to have a huge cluster. One of the statistics that we've got is averages. Average is an interesting one because it's an example of where you need larger data sets to calculate the data. For example, here, in the schema that we've got here, group is like those groups I mentioned, single houses, houses in Norway, or houses in this price range, or houses in this price range in this little valley. And the day is how much traffic on average, or the max traffic, or the min traffic it got on the first day since it got published, or the second day since it got published. So you get these nice graphs. Of course, for some of those groups, like an apartment in this price range in a tiny little valley in Norway, you'd have to run the job over a year or more to get any decent sample size. So this job, too, has to be incremental. And so what we do to make it incremental is we have this TS, timestamp clustering key. And so when we run the job, we run it over the last couple of weeks, and that goes into a data set with a specific timestamp. And when that's finished, we then fold it back into the original data set, which has timestamp 0. And because we have sample size, we can do the weighted folding for those statistics. There's another clustering key here called aggregating since. And that's because we also do sliding windows of averages. You want to see the seasonal changes and changes year by year. We also do user-centric statistics. So for each user, we're collecting signals, or the keywords on the pages that they search for, or the ads that they look at. This information goes into numerous other systems. For example, recommendation systems. In our microservices platform, we use Zipkin. If you haven't heard of Zipkin, it's distributed tracing. It came from Twitter. And it uses the architecture very much the same as ours. It sends all its messages, all its traces, through Scribe, and they go into Cassandra. And it provides you distributed tracing like this. It makes it very easy to performance profile across the microservices architecture. You can also get this graph in the browser with a Zipkin plugin extension. You can see it at the bottom of the screen. We have a Hadoop job written in cascading, which runs once a day and analyzes all of those traces and builds up for us an overview of our microservices platform. And also timestamps it so we can see how the microservices platform is evolving, if there are connections being created which we don't want, or what we should be working on separating out. That job is being submitted as a pull request to the Zipkin project on GitHub. So you're free to go take it. Of course, Hadoop has also come a long way. Yarn has been a fantastic improvement, has changed a lot of things for us. We were already using Pig a lot, but like you've heard in this conference, a lot already, I'm sure. Spark is just fantastic. And Spark integrates really nicely with Hadoop's. Spark isn't good enough yet for us to solve all our use cases. So we're still kind of steady on Hadoop, but the trend is more and more with Spark code being written. For our recommendation system, we have a number of pre-processing jobs generating data sets that we need, and then we run Spark ALS to generate a recommendation model. That seems to generate the best model. But we write that model back in Mahal format. And in the recommendation module, we use Mahal to deliver recommendations. That combination between the two hits a sweet spot for us. Again, this is pretty much all the Spark code that's used to generate the ALS model. It's refreshingly simple and brief. That wraps up the code run through. I've got 2 more slides. The first one is a compliment to the Cassandra community. Like I said, it just keeps on coming leaps and bounds. Some of the things which have really meant a lot for us. Date-tiered compaction strategy, we're already running in that. We have been for 2 weeks in production on 2 different key spaces. One of them didn't work out so well, so we went back to leveled. Another one works really well, just with the default settings. Secondary indexes meant a lot for us. Compression meant a lot for us. CQL3 is fantastic, especially the integration in MapReduce and Spark. Automatic pagination, even though it sounds so simple, it really simplified a lot of code for us. The Fluent API to the SQL Java is brilliant. You know, you can have these hardcore SQL fans sitting next to you, looking over your shoulder, and you're writing your persistence layer in Cassandra, and they're like, damn, I wish my JDBC driver could do that. Counters too, we're not on Cassandra 2.1 yet, but we're really happy that it came through. And as I mentioned before, cross-node timeout and rapid read protection really make a big difference. Last is all the lessons that we've learned. Cassandra is I/O bound, so pay attention to how the disks are running. Have solid monitoring. Go overboard with monitoring. We have Ops Center, we have Munin, we have StatsD and Graphite. In the client pools, we put from the JMX pools, we put that through StatsD and Graphite. We've seen from kernel upgrades, latency on SSD disks go up to 50 millisecond average, and it takes us months to see it because Cassandra is so robust, it just keeps on working. And scale out early. Adding nodes takes capacity, doing repairing or upgrades, they take capacity. You don't want to put yourself into a corner and make those operations way more painful than they need to be. That's me. Looks like I'm on time. Thank you very much. I hope I've given you something to go home with.